Hello class, this is CSE-5250, sections 2 and 60, week 14, spring 2025. So this video was meant to come out last week, but to make sure I had everything absolutely perfect and easy to step through, I had to not only split up the assignment into two parts, but also had to record this at a later date. So this video is for both assignments 2 and 2.5. Two assignments that were originally meant to be one single assignment. So by now you should have gotten the instructions for assignment 2. This also contains the assignment 2.5 instructions. Let's step through the instructions for assignment 2. So this is once again the trapezoid rule, but it's the last time we'll ever be working with the trapezoid rule. To that end, I've also provided for you a pre-written trapezoid rule program, so all you gotta do is swap out the point-to-point communications in the program with collective communications. However, that program isn't quite complete yet, because each process is calculating its own local area, but we need to combine each process's results to get the total area. We need to perform a reduce operation so that we get the total area. There is one other modification we have to do, where if the number of trapezoids isn't divisible by the number of processes, we take the remainder and then add that to one of our processes. That way we get every last trapezoid. So those are the instructions for programming assignment 2. So change the point-to-point communications with collective communication, perform a reduce operation, and then deal with the leftover trapezoids. So you have this. So for your deliverables, you are to, there is a part 0, and that's just running the program. So run the program with 4 processes, take a screenshot of that. That is part 0. There are no deliverables for part 1. Part 2, screenshot the program running with 4 processes. And part 3, screenshot the program using either 3 or 7 processes, and then submit the source code after you have made all the changes described in parts 1, 2, and 3. So those are the instructions for assignment 2. Here are the instructions for assignment 2.5. Here, you're going to write a pi estimating program. Now, unlike the other one where we used an infinite sum to calculate the value of pi, here we're throwing darts at a dartboard. So imagine, if you will, a dartboard on the wall, but that dartboard is on a backing square. You throw darts at this dartboard with the square behind it, and your goal is to randomly throw darts at this square. Some of the darts will land within the circle, some of them will land outside the circle, but within the square, so it'll land within the gaps surrounding the circle. If you throw all those darts uniformly, that is, with enough darts, they're gonna completely and evenly cover the entire dartboard and square. If you take the number of darts that were within the dartboard and then divided it by the number of darts you threw, multiply that by 4, you get the number pi. So this is a Monte Carlo way of calculating the number pi, and it is one of those situations in math where the number pi suddenly comes out of nowhere. So assignment 2.5 has you writing a single process pi estimating program using this Monte Carlo method of estimating the number pi, throwing darts at a dartboard. You are given sample code that you can use to get started. So much of the code is already here. The only main blanks you need to fill in are calculating the random x and y coordinates and calculating the distance from the origin. So, so I talked about the dartboard as being a physical thing. We are now moving it into an abstract mathematical space where instead of a dartboard, it is the unit circle with radius 1, of course, with with that unit circle inscribed within a square of side length 2, also centered on the origin. So both of these are centered on the origin. You throw darts at this square. Some of them will land in the circle. Some of them will land between the gaps between the borders of the circle and the square. Same deal. The number of darts we throw at the square. The number of darts that landed within the circle divided by the number of darts thrown overall, assuming those dart throws were evenly distributed, multiplied by 4, will get us the number pi. So, the calculation for this is pretty simple. We need a random number generator. That way we can generate random xy coordinates. We also need a for loop because, well, we have to, for each for loop iteration, we have to throw a dart. We have to calculate an x and y coordinate and then determine whether those coordinates were within the unit circle. And if they are, we have to increment our darts within the dartboard. After our for loop, we of course have to do the calculation 4 times darts within dartboard divided by darts to throw. That is our estimate for the number of pi. And then we can print that out. So that is part 1. Just simply write out the program listed shown here, fill in the blanks, and run the program. Part 2, you're going to follow this step-by-step process of converting the same program from being a single process program to being an MPI program. So, the steps for this are a bit involved, but they are thorough and hopefully correct. So, one of the things you have to do is make sure that each process has its own unique seed. So that srand time null, we're going to replace that time null with seed, where seed equals time null plus my rank. When we seed our random number generator this way, each process is going to get a seed based on the time. To be absolutely sure each process has its own unique seed, we're going to add my rank, the time null. And then we're going to use that as our seed. Because now we are dividing the work between multiple processes and every process has its own local darts to throw, we now have 2 sets of variables, local and global, or rather total. We also have to calculate whether there is a non-zero remainder and then add that remainder to one of our processes' local darts to throw. We're also going to modify the for loop. So instead of using the original variables, we're going to use the local variables, the local darts to throw and local darts within dartboard. We need to do a reduce operation, so all the local values that each process has, they're gonna get added up and stored in total darts within dartboard in process 0. And then process 0 is going to calculate the estimated value of pi based on the total darts within each process's dartboard. So those are the instructions for part 2 of assignment 2.5. Part 3 is tweaking the program so that it throws 1 million darts and then run the program with a number of darts that does not evenly run the program with a number of processes that does not evenly divide the number of darts. In other words, you're gonna try running this with 1 million darts and 7 processes, because 1 million does not divide by 7 without a remainder. This is to make sure that we are getting every last dart. Recompile and run the program, and then take a screenshot of that output. And as of the deliverables, you have 1 screenshot from part 1, 1 more screenshot from part 2, one more screenshot from part 3 and the source code after you've made all the changes described in parts 1, 2, and 3. If you feel like you got a good handle on what to do for assignments 2 and 2.5, you can basically head off and try it on your own. But if, in case you need some guidance, then keep watching this video. Because we're gonna begin with assignment 2 shortly. We're gonna begin by creating a new C file. Let's call it trap.c, and let's open that, and you can just copy paste the code from the module on Canvas. When I copied and pasted it did not preserve any of the indent levels, so let me go fix that really quick. Okay, there we go. Now the code is all fixed, so you can just download you can instead just download the trap premade.c file that's on Canvas. So this is our pre-made trapezoid rule program. So to make sure this program works, let's go ahead and open the terminal and compile it. So the code has MPI related functions in it, so we have to compile it using MPICC. So MPICC -g -wall -o. It's called trap.c, so we'll name the executable trap. Source code file is trap.c. There we go. Now it gave us a warning, and that's because we have this total area that's unused. We're not using it yet. Let's run this program. So the command for that is mpi exec-n. Let's run it with 4 processes and /trap. Press enter. It's now prompting us to enter A, B, and N. So let's do endpoints 0, 10, and 0, and then 10. So we're finding the area under the curve from endpoints 0 and 10. Let's do 1000 trapezoids. Press enter. And now we have areas between processes 0, 1, 2, and 3. So behind the scenes, we are finding the area under the curve of a function f of x, which is defined to be f of x equals x squared. If you went online and find a area under the curve calculator, if you enter endpoints 0 and 10, you should find that the result should be around 333.3. We can also verify this by punching these 4 values into a calculator. So what's going on behind the scenes is we have divided our interval from 0 to 10 into 2 parts that are each 2.5 units long, and process 0 is calculating the first unit that's between 0 and 2.5. Process 0 is calculating the area from endpoints 0 and 2.5 using 250 trapezoids. Process 1 is 2.5 to 5 using another 250 trapezoids. Process 2 is 5 to 7.5 using 250 trapezoids. Process 3 is 7.5 to 10 using 250 trapezoids. Which also means if we did this with only one process, we get one process calculating the area from endpoints 0 to 10 using all 1000 trapezoids. We have one process, we got the area of 333.3. So it works. But it does not work if we run it with 4 processes. And that's because that work is still divided and we have not reduced it into one process. We have not called reduce yet to get all these values back into one variable. So let's look at the code. So really what we should do is perform that reduce operation. But before that, we should replace these sends and receives with collective communication. So the reason why is, as I had mentioned in the previous video, instead of one process calling send, and then send, and then send, one process sends to two other processes, and then two other processes, those two processes, each send to two other processes. So if we instead send our messages in this tree structure, we effectively send out our message much faster to every process in our communicator. And MPI makes it easy on us by providing a function called MPI bcast. So, how do we replace these sends and receives with one single bcast? Well, we need to do one bcast for every variable we're working with. So, A, B, and N. So let's look at the code for one single bcast. So, MPI bcast. The first thing is the address of variable A. Then, so to recall, the call to bcast requires 5 arguments to be passed in. The first one is the address to the variable containing the data to be broadcasted. The next one is the count. We're only sending one variable, so that's just gonna be 1. The next one is the data type, which is MPI int, since we are broadcasting. It's actually no. We're gonna do 3 broadcasts, and 2 of them are doubles, and the third one is int. So the data type is gonna be MPI double for 2 of the broadcasts, and the third one is MPI int. The fourth argument is the source. So process 0 is the one sending the broadcasting the message, and the fifth argument is the communicator. We're working with the default communicator of MPI com world. So let's fill that out. So, by the way, it is process 0 that is handling user input. So if my rank equals 0, prompt the user for user input, and then send that information to all other processes. Otherwise, receive a message from process 0. So to signify those changes, I'm gonna comment out all of these sends and the for loop, and then I'm also gonna comment out these receives. Because every process is gonna call bcast, I'm gonna put the broadcast outside of this code here. So all this code is basically gone. We don't even need this else anymore. So I could probably comment out that line too. I just gotta make sure that these curly brackets are matching. So really the only code that is going to differ between processes is this code here that only process 0 is gonna execute. Everything else, gone. I can even go so far as to just delete all that code right then and there. But let's fill in that broadcast to replace these lines of code. So bcast address of A, 1. This is a double. So the data type is MPI double. The sending process is process 0, and we're gonna work with the communicator, the default communicator, MPI com world. And there we go. So that's one variable, but we need the other 2. So I'll just copy this line of code, paste it twice. This is now for B, and then N. So both variables A and B, those are of type double, but N is of type int. So this third one should be MPI int. There we go. So with that, let's for fun run this program. Let's recompile and rerun this program to make sure we are getting the same result. So take a mental note of these outputs here. We should get 5, 98, 192, and 36. Not necessarily in that order. So I'm going to recompile the program. Okay, so now we have a destination variable that's unused. So for the sake of clean code, I'm just going to comment out this destination variable here that was previously used for the for loop in here that we're not using anymore. So I'm going to comment out that destination one. We're still not using the total area variable just yet. Let me just recompile it to make sure. Now the only warning left is the total area variable not being used. Ignore that for now, we're going to proceed. So npi exec-n for./trap. With our program recompiled, let's run it. Okay, so enter A, B, and N. So same endpoints as before, 0, 10, and same number of trapezoids as before, 1000. Press enter. And now we have the same results as we did before. 98, 5, 36, and 192. Not necessarily in that order, but we still have the same for areas as before. It worked. But now we need to do a reduce, which is the reverse of a broadcast. So let's do that right now. So this is actually the next to do here. So it's actually the last one. We are gonna tackle this one after that. Okay, so we need to perform a reduce operation. Let's just erase that to signify that we're done with that. Now we need to perform a reduce operation and print out the total area. So the reduce operation has 1, 2, 3, 4, 5, 6, 7 arguments to be passed in. So the first argument is the, I guess think of it as the outgoing data. So we're gonna pass in the address to the variable that contains our outgoing data. Next, we pass in the address of the total area variable. So what's going on is each process has its own variable called local area, but each process also has a variable also called total area. It's only process 0 that's working with the variable called total area. So one of the rules is with reduce, every process must pass in something for the second argument, even if it must pass in null. For the sake of consistency, every process is going to pass in local area for the first argument. Every process is going to pass in total area for the second argument, even though it's only process 0 that's going to be working with the total area. We only have one value to send, so we'll pass in 1 for the third argument. This is of data type double, so MPI double. We're doing addition as our reduction operation, so MPI sum. For the fifth argument, process 0 is the process that's receiving all these values, and we are working with the default communicator MPI comworld. There we go. Now the last step is to print out that result. So if my rank equals 0, again, code like that is a hallmark of SPMD programming, where we have one process do something specific from the others. In this case, it's process 0 that's going to print out the area. The total area is %f \n, quotation mark, and total area. There we go. Let's clear the terminal and recompile our program. There we go. Now we have no errors because every last variable is being used. So let's run this thing again. So MPI exec, enter A, B, and N. I'm gonna use the same values as before, 0, 10, and 1000. Press enter. Now we have the total area of 333.3335. If I did this again with only one process, then we get process 0 calculating the total area, and there's only one process, so. But process zero's area and the total area are going to be the same, we got the same result. It works! One other thing we have to do is to make sure that we have every last trapezoid being added to our area. So if we have a number of processes that does not evenly divide the number of trapezoids, we're going to make sure that those remainder trapezoids are added. So let's work on this last to-do. Check whether dividing n by com size results in a non-zero remainder, and then add those missing trapezoids to, let's add it to the last process. So this is the code. This is code that we had to add in one of our previous forays into the trapezoid. So this is going to be pretty simple. If my rank equals com size minus 1, int remainder equals n mod com size, where n is the number of trapezoids, and then local n plus equals remainder. And that's it. Well, technically we could have this added to any process. We could add it to the first process if you wanted to. That would be process 0. I'm just adding it to the last process because, well, it's basically arbitrary. I'm just using the last process as an example. Okay? Now, let's run our program, but instead, let's run it with a number of processes that does not divide 1000 without a remainder. So, let's recompile the program once more. Okay, hold on. Let's see. Local in may be uninitialized. Okay, hold on. Let me see. Let me debug this really quick. Okay, I think I found the issue. I have to... So there's an error with the pre-made code where looks like I put the to-do in the wrong place, so I have to go fix that as well. So let's recompile that. Okay, now we have no issues. So, yeah, the code, or rather the to-do, should actually be after these 3 lines of code. So now we have our code in the right place. Let's try this once again. Okay, so now I have the code compiled. Let's run it once more. npm exec 010 1000. Okay, it runs just fine, but really I want to run it with, say, 7 processes. Okay, now I have that message where it says not enough slots. Let's fix that up by adding oversubscribe to it. There we go. 010 1000, and we still get the same area as before, but not quite. Is this because we're still getting value trapezoids being lost? No, because we still got the same value as we did the last time. At this point, it may very well be just floating point errors changing our result. One of the weird things about floating point arithmetic is that it isn't associative. So the order in which you do your additions might affect the overall result. So for our purposes, we're gonna call this complete. I have to go edit the, I have to go make some corrections to your pre-made trapezoid rule program, but hopefully by the time you see this, those changes will have since been made. So those are the instructions for your assignment 2. Let's work on assignment 2.5 now. Alright, let me close these real quick. So at each point of our additions, we need to make screenshots. So those are going to be part of your deliverables for assignment 2. Let's look at your pi estimating program. So So let me make a brand new file. I'm gonna do this the one way I know how. That is vi pi.c escape:wq. So now I have a new file made here. Let's open that. And now, let's start writing the code for our pi estimating program. So, let me put this on one of my other monitors, because of course I would have multiple monitors. It just helps with seeing everything that I'm working on. Okay? Let's begin writing the code. So, oops. Alright, here we go. Here is part 1. Let's begin with writing the pi estimating program. So, include standard io.h, and include time.h, include standard lib.h, include math.h. So in a little bit, I'll show you how that last one might not be necessary, but if you do include it, it might have a few hiccups. Let's proceed with the code. Give me a minute. So the first thing we need to do is we need a random number generator, and before we can use it, we have to seed it. There's several ways we can make a random number generator. We're just gonna go with using srand. So srand, we pass in time, null. This uses the current time as a seed for the random number generator. How is the time encoded? Well, it's encoded as the number of seconds since January 1st, 1970. Yeah, so it's a number of seconds since that date. That is the time that's being used for our seed for our random number generator. Let's continue. So we need two variables, int darts within dartboard. We're going to set that to 0. We also need another variable, int darts to throw. We're going to set that to, let's start with drawing 10,000 darts. There we go. And now we need a for loop. So for int I equals 0, I is less than darts to throw I plus plus. Next, we need to generate a random xy coordinate where x and y are within the range -1, 0, positive 1.0. There we go. So now we are generating two random numbers between -1 and +1, but we need two of them to create our random xy coordinate. So let's declare two variables. Double rand x and rand y. Let's assign rand x to calculate a random number between x and y. So typically when you work with random number generators, you're probably generating random integers, but we want a random float. So how do we do that? Well, this random number generator is going to randomly generate an integer, but if we want to convert that into a float, we're going to divide that by something called randmax. So when we generate a random number generator, so when we seed a random number generator, after that we can call rand to get a random number. And this will create a random number between, well, it's going to create a random, yeah, it's just going to create a random number, but we want this to be between 0, no, not 0, rather -1 and +1. So when we call rand, that's not enough. We have to divide it by rand max. So now, by doing that, it's going to create a random number between... Hold on. Okay, so when we call rand, it's going to generate some number between 0 and random max. When we divide that by random max, it's going to convert it to a random value from 0.0 and 1.0. However, we need to cast this to a double, so that way, instead of being interpreted as integer division, it's going to be interpreted as floating point division. We're not done yet. We have to multiply this whole value by 2. So that way, instead of being a random number from 0 to 1, a random double from 0 to 1, it's now a random double from 0 to 2. But we're not done yet. We still need to subtract 1.0, so that way, it's finally a random number between -1.0 and +1.0. So that's how we get a random floating point value. We call rand, we cast it to double, divide that rand by rand max, and for our purposes, because we want a random double between -1 and +1, we multiply this by we multiply this by 2, and then subtract 1, and now we get a random double between -1 and +1. We need to do this twice because we have both a x value and a y value. So I'll just duplicate that and replace that, and then change that to random y. Now we have our random coordinates. All done. Let's proceed to our next step. And this next step is optional, but let's just print out the coordinates. Process has created random coordinates, and we're going to pass in rand x, rand y. Eventually, we're going to have to comment that out because it's going to eventually get in the way. Alright, our next step is to calculate the distance between 0 and the coordinates x, y. And we're going to use the distance formula for that, which is, because we're going to find the distance between 0, 0 and xy, for the distance formula, we have to find the difference between the two x's and then the difference between the two y's. Since it doesn't matter the order in which we subtract one from the other, and one of those values is 0, we can just do this. We can just simply say dist equals rand x times rand x plus rand y times rand y. Of course, we need to take the square root of that, and I included the math.h. I included math.h up here, and that's because that contains square root. There we go. Technically, you don't even need to take the square root, because we want to determine whether the distance between these 2 points is less than or equal to 1. If we squared it, if we just left it squared, it doesn't matter because 1 squared equals 1. So really, this square root isn't really necessary. I'm just including it anyway just for the sake of completion, but per the instructions in the textbook, it doesn't even use the square root function. Matter of fact, when I tried to compile this earlier, I had an issue where it couldn't find the square root function, and I had to add -lm to the command to compile it. I'm just taking the square root just for the sake of completion. If anything, in the past times I've shown how to make this program, I've never even used the square root of this value. But I'm just doing it for the sake of completion. Now that we have our distance, let's check whether it's less than or equal to 1. So if distance is less than or equal to 1.0, if it is less than or equal to 1.0, we're gonna increment our darts within dartboard variable by 1. So copy that, paste, ++. There we go. And that right there is the code for the for loop. We're almost done. We just gotta add in the code to print out the result for pi. So double pi estimate equals 4.0 times darts within dartboard divided by darts to row. Printf. There we go. That is our estimated value of pi. Return 0. And that's the end of our program. So we need to multiply by 4.0 to ensure that once this times this is evaluated, it then gets interpreted as floating point division, not integer division. Alright, so now with all those changes, so with all that code written, let's compile it. So there is no MPI code yet, so we can just do gcc-o. It's called pi.c, so let's call the executable pi. The source code file is pi.c. Press enter. Okay, distance is undeclared. Okay, so that is an error. Really quick, I'll just add in double dist. There we go. Let's recompile that. Okay, so that is the issue I was talking about. It does not know what square root is. So to fix that, I have to add -lm to the command here. Press enter. There we go. If you still can't get the square root to work, you can just go forward without the square root. Just write it like that. It will still work. So, if you want to use the square root like I'm doing here, you need to add -lm to the end of your command. That way the compiler knows where to find the square root function. So with that, let's run our program. /pi. So that was like that was 10,000 random coordinates being generated, where x and y are between -1 and +1. That is a lot of coordinates. And now we have our estimated value of pi being 3.1348, which is not quite correct. But here's the thing. If we throw more darts at our dartboard, we get a better approximation for pi. So let's try that. So let's recompile our program and then rerun it. 3.1419 141,491. Should be 3.14159. But we're getting a better estimate. If we throw even more darts, I'll just type in 1E9 as a shorthand for 1 billion. Clear. I had mentioned previously that we had to comment out this line here that prints out the random coordinates once we get to numbers of darts that are in the billions. Yeah, you have to comment it out. It's just going to get in the way. So let's recompile our program real quick, and then rerun it. It's probably going to take some time because that is a lot of darts we have to throw. So, I guess now we wait. Well, that took a while. So, this is probably why we want to start parallelizing the program, because once we get to these large dart amounts, we want to parallelize the program. Okay, so now we have a still not good estimate for pi, but, well, we tried. Okay, so we have our one process program. So with this code now written, what I'm going to do is, okay, that's just the pre-made version from earlier, from when I was making the instructions. I'm going to take this program, copy paste it, and I'll rename the copy pi2. I'm going to open this one, and now we can edit our program. So with this program, just compile the program and then take a screenshot of the output. So let's begin at looking at our next step, where we take the program and parallelize it. So now we get to add MPI related functions to our entire program. So I'm going to do this to the copy here. I'm going to close this right now, and now let's begin. We need to, of course, include MPI.h. Now, we need to add the preliminary function calls related to MPI. So first we need to create two variables, int my rank and com size. Next we need to call MPI init, pass in null for that. We need to call MPI com size, pass in MPI com world, and then the address of com size, and MPI com rank, pass an MPI com world, and address of my rank. There we go. And now let's address that random number generator. If we proceed with this random number generator as it is. In my testing, I have found that when this program runs, every process that's created will have the same seed. And for our purposes, we don't want that, so I'm going to modify this code so we have a variable called seed, and it is equal to time null plus my rank. This way, every process has its own seed. We're gonna then replace this srn time null with srn seed. Again, we want to give each process its own seed, so that way it isn't the same program being run like 8 or 16 times or 1,000,000 times. Either it's 1,000,000 programs, but they each have their own seed. That means they have their own slightly different numbers of darts being thrown at their own dartboard. Speaking of which, well, before we get to dealing with these variables, this is just an optional step. Print out the seed. Printf percent. Okay. Process percent d's seed is percent d \n my rank seed. There we go. Okay. So as it stands, this is just going to be multiple instances of the same program, and had we not changed the seed, it would be multiple instances of the same program, each giving the same result. The reason why you wanted to give each process its own seed, so that it would be multiple instances of the same program, but with different seeds. Therefore, each process would have a different number of darts thrown within the dartboard. However, we want to divide the number of darts being thrown among all of our processes. So, let's do that. So, to signify these changes, this darts within dartboard, let's replace that with, well, actually, let's replace that with two variables. Local darts within dartboard and total darts within dartboard. Next, we need two things. Total darts to throw and a local darts to throw. And we're going to calculate local darts to throw as being total darts to throw divided by com size. So that way, the number of darts being thrown is evenly divided between all of our processes within our communicator. However, this is going to be subject to the same issue as with the trapezoid rule, where if the number of darts cannot be divided evenly by the number of processes, there might be some darts being lost. So let's add some code to make sure we get every last dart. If my rank equals com size minus 1, let's calculate the remainder. Int remainder equals total darts to throw mod com size, and then local darts to throw plus equals remainder. So this is code that's only going to be executed by the last process in our communicator. Okay, I just arbitrarily chose the last process. It could be the first process of process 0. Doesn't matter. It will work either way. So, again, this is to make sure we get every last dart, even if the number of processes does not evenly divide the number of darts. Alright, so now we can start throwing darts at our virtual dartboard. However, we cannot use the variable darts to throw anymore. We renamed it. So, we have to rename this to local darts to throw. Because we divided the number of darts between our processes. Each process must throw their own set of darts one by one. So, local darts to throw. The calculation for random x and y coordinates is still the same, except now when we check whether the distance is less than or equal to 1, we increment local darts within dartboard. Because so far, because all this code is being executed by every process is going to calculate its own number of darts thrown within their dartboards. But eventually we need to do a reduction operation to get those local values added together and stored within a global value, a global variable. I'm going to add this extra line of code for debugging purposes. And that code is going to be printf process %d has thrown %d out of %d darts within the dartboard. And I'm going to pass in my rank local darts within dartboard and local darts to throw. There we go. So now, what used to be an operation being done by one process is now being divided between multiple processes. So we have local versions of the same variable and global versions of the same variable. It's only going to be process 0 that's going to work with the global versions of those variables, total darts to throw and total darts within dartboard. Let's work at that. Let's work with that one next. So, next we have to perform a reduce operation. So that is MPI reduce. We pass in the address of local darts within dartboard as our source, and total darts within dartboard as our destination. Next, we pass in 1 because we're only sending one value, MPI int because that's the data type, it's an integer value, MPI sum because that's our reduction operation, 0 because the process that's going to hold the destination process is going to be 0, process 0, and MPI com world because we're working with the default communicator. Now we just got to modify this print code where it's only going to be process 0 that prints out the result. If my rank equals 0, it's only process 0 that's going to print out the result. So let's just fix up that code. So we're going to still have a pi estimate, but we can't use the variables darts within dartboard and darts to throw anymore because those don't exist anymore. We renamed them. So now we have total darts to throw and total darts within dartboard. So our pi estimate is going to be the total darts within dartboard and divided by the total darts to throw, which we declared these variables all the way up here, so we have the locals and the totals. And now we can just print out that result. We're almost done. We just gotta print. Now that we have printed out our estimate for pi, we can call MPI finalize. There we go. So now we have our program hopefully complete. Because now we have MPI related stuff, we need to compile this using MPI-CC. MPI-CC-G-wall-O. The program is called pi2. The source code file is pi2.c. And because I'm using that square root function, I have to add -lm to the command. There we go. It compiled. Let's run it. So that is MPI exec-n. Let's do 4 processes. And let's run it with one more change I should have done earlier. I need to change this back to 1 million darts. So there we go, 1 million darts. Because 1 billion was a lot. So really I need to recompile the program again. So now let's run this program. MPI exec-n. Let's do 4 processes and /pi2. Press enter. We see that each process has its own seed, and therefore each process has slightly different amounts of darts that landed within their respective dartboards. Process 2 has thrown 196,022 darts. Process 1, 196,725 darts. Process 3, 196,232 darts. Process 0, 196,367 darts. And they each drew 250,000 darts because, well, we have 1 million darts to throw. Divided between those 4 processes. And now, we have an estimate for pi for 3.14384. Still not good, but hey, it's getting there. So, we actually did one change a bit too early, and that value of 1 million should have been 10,000. So now that we've made our change a little bit too early, let's actually look at part 3, where we changed the number of darts to throw to 1 million, but now we've already done it. So let's run our program with a number of processes that doesn't divide 1 million. So let's do 7 processes, and because this is more slots than this is more processes than there are slots available on my machine, I have to add the oversubscribe tag. There we go. So check this out. Each process is throwing 142,857 darts. All but one of them, which is throwing 142,858 darts. Each process is throwing about 112,000 darts each. Those values here are being added together by our reduce operation, and then our process 0 is printing out the estimate for pi. Let's really make sure that this reduce operation is working. So let's do this. Again, this is just yet another optional step. Okay, so that's just an extra step that isn't in the instructions. I'm just adding it just for the sake of clarity. Let's recompile the program. There we go. Okay, data type mismatch. That should be %D. There we go. Fixed it. Recompile, clear, and let's recompile it with 7 processes. There we go. It worked. So we have 785,000 darts that were within the dartboard total. And we get an answer for pi of 3.140896, which is not quite right, but again, the more darts we throw, the better the estimate. So our program works. Nice. So for the deliverables for assignment 2.5, part 1, just take a screenshot of the program running. Part 2, screenshot of the program running with 4 processes. Part 3, screenshot of the program running with a number of processes that does not evenly divide the number of darts. For example, do 1 million darts and 7 processes. And then, also part of part 3, the source code after all changes described in parts 1, 2, and 3. So that is the instructions for your last programming assignment. That means the last thing after that is going to be your final project. Once you have written the code for this project, we're going to benchmark it. So there are going to be a few more changes that we have to do as part of your final project, but I'll get to that once we actually get to the final project. In the meantime, complete assignments 2 and 2.5, submit your results, and sometime next week, we're gonna get to work on benchmarking this pi estimating program. Not the trapezoid rule, because we're probably sick of working with the trapezoid rule by now. We're gonna work with the pi estimating program now. Okay? Alright. So, we'll talk about the final project sometime next week. And yeah. Have a good one, and I'll probably see you for the last time next week. Have a good one. Take care, and see you next time.